One of the recurring problems that we have in astronomy is trying to figure out how far away stuff is. We've mentioned this previously, but again, when you just look up at the sky and you see stars, you really have no idea how far away they actually are. It's the exact same problem even with photographs of the sky. We take a picture, we still don't know exactly how far away things are just by looking at it. Now, we did mention previously that we can start to get an idea of distances using stellar parallax, this idea that as the Earth goes around the Sun, we see the stars shift a little bit in the sky. And that's one way we have of figuring out distances to these things. But stellar parallax is only going to work so far away from the Earth. Once the things get too far away, the motion gets so small we can't measure it anymore. So we've only got this little bubble around us where we can use stellar parallax. What this means is we have to come up with other and clever ways to figure out distances to other objects. This leads us to our third lecture quiz question. What do we need to determine distance? A, mass, B, temperature, C, color, or D, luminosity? Go ahead and think about it and we'll discuss in just a bit. Alright, so to figure out distance, we need D, luminosity. We determine the luminosity, which is the total energy output of the object, and then we compare it to the brightness, how much of that energy we get, and that tells us how far away it is. So the correct answer is D, luminosity. So knowing that we need to have these objects of a known luminosity, we have the idea of a standard candle. A standard candle is an object where we know the luminosity. A good standard candle has four properties. First, it needs to be very luminous. We want it to be very luminous because the more luminous it is, the farther away we're still going to be able to see it. So the more luminous it is, the greater distances we can figure out. Second, we need to be certain of its luminosity. If there's any guess or error in determining the luminosity, then there's guess and error in figuring out the distance. So the better we know the luminosity, the better we're going to determine distance. Third, they should be easily identifiable. If you can't be absolutely certain of the thing that you're looking at, if it can be easily confused with some other object, then you don't actually know what you're looking at, and therefore you don't actually know the distance. Therefore, we need to make sure we can tell what it is. And then fourth, it needs to be common, so that no matter where we look in the sky or out in space, we're going to be able to find it so that we can figure out distances. One type of standard candle are actually main sequence stars. We kind of touched on this previously when talking about the main sequence, but the idea is that as long as we know the stars on the main sequence, then once we determine the spectral type, we know the luminosity. So, as an example, our Sun is a G2 star. So, if we find another G2 star that's on the main sequence, then it's going to have the exact same position as our Sun, and therefore we already know the luminosity. So, as long as we know what's on the main sequence and we can determine spectral type, we can figure out luminosity and therefore distance. Figuring out distance in this way is known as main sequence fitting, if you're using as much of the main sequence as a cluster still has, or spectroscopic parallax, because we're using the spectrum to determine the spectral type, which we can then use to figure out luminosity. Some other examples of standard candles that we've already talked about are RR Lyrae variables, Cepheid variables, and type 1a supernova. So we talked about RR Lyrae variables previously when talking about figuring out the size and our position within the Milky Way galaxy. These are the variable stars that were used to figure out the distances within globular clusters. Okay, so these are the smaller stars that pulsate in and out, and that pulsation period allows us to figure out the luminosity. The bigger brother to the RR Lyrae are the Cepheid variables. Because these are larger, they are more luminous, which means we don't just see them out in the halo of our own Milky Way, we can actually identify them in nearby galaxies. So remember, the Cepheid variable is actually what Hubble used to figure out the distance to Andromeda and to start figuring out distances to these other nearby galaxies. We can also use type 1a supernovae. So remember, type 1a is the weird type. It's the one where a white dwarf has gained too much mass and explodes. Because it is a supernova, these are going to be very luminous. We can actually see these out to around 3 billion light years, so really distant. Now, there are some slight complications with type 1a because they're not all exactly the same luminosity. However, we have figured out relationships on how long it takes for it to dim and the way it dims to the peak luminosity, which means we can still figure out the luminosity, although there is still some error in these measurements. Now, one approach that did not use a standard candle was developed in the 1970s. Instead of using a standard candle, this looked at the 21 centimeter radio emission from neutral hydrogen of spiral-type galaxies. So the 21 centimeter line is given off by the interstellar medium. So the idea is that these spiral galaxies will be rotating. And because they're rotating, we're going to get a red shift and a blue shift for this 21 centimeter line. Now, the faster that the galaxy rotates, the wider that spread becomes. Okay, the bigger difference between the red and blue shift. So what we do is we look at the width of the 21 centimeter line. That is then related to how fast the galaxy is rotating. How fast the galaxy is rotating is then related to how much mass is inside the galaxy, how much gravity is pulling in on it. How much mass there is going to be related to how many stars, and how many stars is then related to the luminosity. From luminosity, we can figure out distance. Okay, so this whole process is what's known as the Tully-Fisher relation, named after the two astronomers who figured this all out. We actually have another way of determining distance to other galaxies without using a standard candle. This was in part developed by Hubble and other astronomers in the 1920s. So we get this idea that there are other galaxies out there, and at first we wanted to figure out what is the nature of them, what are these things, period, and then once we established they are galaxies, we wanted to figure out more about them. So we began taking the full spectrum, spreading out all the light to see what we could see. Well, what they noticed is that most galaxies are red-shifted, meaning that they're going to be moving away from us. This general motion of galaxies away from us is what is known as the Hubble flow. Well, after figuring out the distance to these galaxies, they noticed an interesting relationship. Specifically, the farther away the galaxy is, the more red-shifted it is. So the farther away it is, the faster it's going to be moving away from us. So on this graph, up and down, we're looking at how fast it's moving, so the velocity, and then along the bottom, we're looking at the distance. Notice that all of these galaxies are very close to this line. What this means is we can then form a relationship. This is what's known as Hubble's law. How fast the velocity it's moving away from us is equal to the slope of this line, which is known as Hubble's constant, times its distance. What this means is if we can figure out how fast it's moving away, we can then figure out the distance to that galaxy as long as we know the value for the Hubble constant. The primary mission of the Hubble Space Telescope was actually to get a good value for the Hubble constant. The currently accepted value for the Hubble constant is somewhere around 70 kilometers per second per megaparsec. No, you don't actually have to know that value. I just like that we do know it. Now, all of these different ways of determining distance can actually be summarized on what we refer to as the distance ladder. Now, the reason why we call it a ladder is because the next step we take in figuring out the distance to things is always determined by what we learned in the previous step. So, as an example, the first thing we had to figure out distances was parallax, and that gets us this bubble around the Earth. But there were enough stars within this bubble of parallax that it allowed us to start using things like main sequence fitting and spectroscopic parallax, using main sequence stars as standard candles. That then extended things out to include a lot of the Milky Way, and then from that there was enough stuff that we could figure out other things like RR Lyrae variables and Cepheid variables. Well, with Cepheid variables, that pushes us out farther to the point that we're now including other galaxies, not just our own. And with all of that information, we can then figure things out like the Tully-Fisher relation, Hubble's law, and white dwarf supernovae. So we keep stepping out to greater and greater distance based on everything that we learned previously.